Hey everybody, it's Ripley again. We're going to talk about section 4.3 today, and it's basically derivatives of functions and what it makes f of x look like. In other words, what is the derivative of a function? How does it affect what f of x does? But before we do that, we got to talk about something called the mean value theorem. It's the last of our value theorems. Okay, if you recall, by the way, this is shorthand as MVT. If you recall, there's the intermediate value theorem, which starts out if f is a continuous function on a closed interval, then between any 2 points, f has to pass through all of those values of f. The extreme value theorem says that if f is a continuous function on a closed interval, then that function has to have both an absolute max and an absolute min. And then last but not least, there's the mean value theorem. Now, the little presumption here is a little bit, it's a little more detailed. Let me show you what it says. It says, suppose that f of x is differentiable on a closed interval. Okay, now notice, differentiable, that's a little more specific, isn't it? Differentiable still implies continuous, so I can write this sort of parenthetically up here. I can write this as continuous, because we know that all differentiable functions are continuous, right, on the interval. If they're differentiable on the interval, then they have to be continuous on the interval. But we need a little bit more moxie here, okay? Excuse me. So we've got this continuously differentiable function on a closed interval from a to b. All right, then there must be, let's put a little an implies arrow here. There must be a c in the open interval from a to b such that f primed of c equals f of b minus f of a over b minus a. Now, look at what that really says. It says, if I take a function on a closed interval, all right, so let's close this thing out. Let's call this a, and let's call this b. All right, and oh, by the way, this c, think of this c not just as a c, but this is at least one such c. And I'll show you what I mean by that. All right, now this point right here is a f of a, and this point right here is b f of b. Now, let's make sure, I'm going to sneeze, excuse me, we understand what's going on. What is f of b minus f of a over b minus a? Well, hopefully you guys recognize that as being the slope of the secant line. So if I draw a secant line, I know that the slope of that line, so I'll do this at m equals f of b minus f of a over b minus a. Now, what does the mean value theorem say? What it really says is that at least one point, so some c, now look at that, f primed of c. Well, what is f primed of anything? Remember, this is the slope of tangent lines. In other words, there must be at least one tangent line that has the exact same slope. Now, it appears with my drawing that there appear to be, this is bad because it doesn't look too terribly smooth, but there appear to be two such places. But remember, the mean value theorem guarantees at least one. Notice that c lives in between them. So let's say, for example, show the mean value theorem holds true for f of x equals x squared on, I don't know, let's go 1 to 5. Whoops, that should be closed, right? All right, so first and foremost, let's make sure that we satisfy the beginning of the theorem. Well, it's the function x squared. We know that's continuous. It's on a closed interval. All right, now we need to find some value, so we're just going to call this some c that's an element of the open interval from 1 to 5 such that, now what? Well, we just got to satisfy this, right? F primed of c, which is equal to what? Well, f primed of x, let's just put some notes up here, is equal to 2x. So f primed of c is equal to 2x. nothing to it. Whoops, not 2x, 2c. All right, because we want to be as true to the theorem as we can, otherwise we'll get ourselves confused. F prime of c is 2c equals f of b, so this is going to be f of 5 minus f of 1 over 5 minus 1. So 2c is equal to 25 minus 1 over 5 minus 1, affectionately known as 24/4, affectionately known as 6, which implies that c equals 3. Now let's look at this, even with a really badly drawn function, which we know I'm capable of. All right, so let's just for giggles, let's call this 5. Let's call this 1. All right, so what we're saying is, with a really poorly drawn function, if I connect those points, the slope of that is f of 5 minus f of 1 over 5 minus 1. Standard issue Algebra 1 stuff. And apparently, according to the mean value theorem over here at 3, now let's check it out. If I draw the tangent line, I mean, it's a bad function. It's badly drawn, but I still get pretty darn close, don't I? I mean, check that out. Whoa, my eraser's getting jukey. Okay, right there. Perfect. We satisfied it. Nothing to it. So what's the moral of the story? When you're dealing with mean value theorem, take the derivative. It's the first thing you're going to do. Plug c into it, find the slope of the secant line, and then solve for the value of c that makes the derivative at c and the secant line equal. Done. Really, really simple. Okay? All right, let's move on. We're going to play with derivatives, and I'm going to give you a very powerful tool called a Ripley-Doodle diagram. This is my egomaniacal way of interjecting my megalomaniac personality into my lectures. So we're going to talk about Ripley-Doodle diagrams. Now, a Ripley-Doodle diagram is not legal on an AP exam. The technical name, for those of you splitting hairs out there, is called a sign chart. All right? You're not allowed to use these as proof on the AP exam. So I'm going to wean you off of them down the road, but for now they're very, very useful. They're very helpful. Okay? Now, watch. I'm going to do this. It's going to be, I'm going to instruct you by doing a problem. I'm going to let f of x equal, I don't know, let's let it be 3x. It's got to be a good one. We'll make it be a good polygon. Minus 4x cubed. I'm going to simplify it so I stay out of my own way a little bit here. X squared plus 5. Okay? And I'm going to find the following. We'll put them over here. I want to know when is f of x, and then we'll go increasing, decreasing. Let's go max and mins. Okay, when and where are they? Let's go concave up, 3, what's 4, 5, what's going on? I've suddenly started counting backwards. Concave down, and then hopefully you remember those inflection points. Remember what an inflection point is? It's a point on the curve where the function changes concavity. All right, so we're going to do all of this, and then let's do a sketch, just for giggles. All right, and then we'll throw it in our calculator, and we'll see how close we got. So first things first, think about this. How can I tell when a function's increasing? Well, way back when, that was when f prime of x was greater than 0, right? Well, let's take a derivative and see what happens. F prime of x equals 12x cubed minus 12x squared minus 24x. Do you agree with that? Now, what do we do with this? Well, hopefully you remember from last section that there are these things called critical points or critical values. And in those things, what we did is we took derivatives and we set them equal to 0 because magical things seem to happen around our zeros. With the employ of this new Ripley-Doodle diagram, you'll see that not only do magical things happen at the zeros, but they happen around the zeros. All right? So here we go. Let's set it equal to 0. I'm going to solve for critical values. So it appears as though I can factor out a 12x. Oops, got a little crazy with my parentheses there. Sorry about that. So I'm going to factor out a 12x. Why am I doing this? Because then it tells me the values of x for which this thing equals 0, right? So I end up with what? X squared minus x minus 2 equals 0. Let's do a little more dirt work. 12x, and I'm going to get x minus 2 and x plus 1 equals 0. Guess what? I have critical points at x equals where? I get 1 from 0 here. That's cool. I get 1 at -1 here, and then I get 1 at +2 here. Look at that. Those are my critical points. Now, for those of you that had me for Algebra 2, we've already used these before, but that number is dwindling quickly. They're getting few and far between. I am going to use a Ripley-Doodle diagram. Now, I do want to throw a little caveat in here. I think a lot of us are very, very used to like dividing out this 12, getting rid of weird factors, because you got this 0 here. It's like, ooh, I can get rid of superfluous information. In calculus, keep everything. And I'll show you why here in just a sec with this example. Now, I'm going to notice I label my Ripley-Doodle diagram. If I don't label my Ripley-Doodle diagram, it's a simple number line and it tells me no information. And I will pop you for that. If you have these sign charts or these Ripley-Doodle diagrams without labels on them, I'm going to land on you, because otherwise they mean nothing. They are a mathematical jellyfish. Okay? So I'm going to stick -1 on here. I'm going to stick 0 on here. And I'm going to stick 2 on here. Don't worry about scale. Okay? Now, the idea here is keep your eye on the prize. Think about f primed of x. That's really important. This line is supposed to represent the signs of f primed of x. So what I'm going to do is I'm going to plug values in between each one of these critical points, and I'll change signs. All right. So now notice I don't care about the number. I care about its sign. So I'm going to pick a value to the left of -1. Let's say x equals -10,000. Well, it's definitely left of -1, right? If I plug -10,000 into here, I get a negative, right? For sure, for the 12x. If I plug it into here, I get another negative. And if I plug it into here, I get another negative. Now, you'll do this all in your head as you get better and better at this. Okay? So it appears that when I'm to the left of -1, that my derivative is always going to be negative. So I'm going to slap that on my Ripley-Doodle diagram. Okay, it's a negative. Now you may say, wait, how do I know that something funky didn't happen between -1 and -10,000? Well, if it did, I would have picked up another critical point. All right, so can you think of a good value between -1 and 0? How about x equals negative, whoops, I'm going to work my way down here. How about x equals -1/2? Now again, you'll be doing these in your head down the road. If I plug -1/2 into here, I get a negative. If I plug it into here, I get a negative. And if I plug it into here, I get a positive, don't I? So a negative times a negative times a positive is a positive. Let's pick a value between 0 and 2. How about x equals 1? If I plug that into here now, I get a positive. If I plug it into here, I get a negative. And if I plug it into here, I get a positive. Now don't get cocky. It's not always going to change signs like it's doing. We just got lucky. Okay, and last but not least, let's pick a value to the right of 2. How about x equals 5,000? It's definitely a value to the right of 2, right? If I plug it in here, I get a positive. If I plug it in here, I get a positive. And if I plug it in here, I get a positive. Guess what? Now, what does that tell me? Look at this. I'm already halfway done. Remember back in the day, we discovered that if the first derivative is negative, what's the function doing? It's decreasing. So I know that it's decreasing from -∞ to -1. If the first derivative is positive, what's the function doing? It's increasing, right? This is f of x. I should definitely, all right, then f of x is decreasing when the first derivative is negative. It's increasing when the first derivative is positive. So again, I've got a decreasing here and an increasing here. And guess what? I can already build a stick figure of f of x based on this Ripley-Doodle diagram. I know it goes down, it levels off. How do I know it levels off? Because I know the first derivative when x equals -1 equals 0. It goes up, it levels off again, because the first derivative is 0 at 0. It goes down, it levels off at 2, wow, and then it goes up again. So I know it's going to have this basic shape. That's what it's going to look like. But more importantly, check it out. I can now fill in a whole bunch of my information. All right, let's do increasing. Well, when's it increasing? Well, it appears from -1 to 0 for sure. Now, it's neither increasing nor decreasing at